In the last video, we performed sort of a general root finding procedure. We got a new function, we plotted it, we searched it, and then we refined the roots. And we found 4 of them. We saw that that first root was converging very slowly, and we hypothesized that it's something to do with being nonlinear, maybe. So in this video, we're going to visualize the secant method, and we'll visualize that same function at that first root where we were having troubles. So let's go ahead and get started, and we'll start all over. Start with a new script file, and the first line I like to name the function. What should we call this? How about visualize secant method dot m, and what I'll do is I will select that, copy, save as, and I will paste, and there we go. So now when I hit run, it automatically saves this script file and runs it. And you can see where MATLAB automatically typed in the name of the file over here for us to run it. So the first thing I like to do is initialize MATLAB. So we will close any open figure window. We will clear the command window to the right. And then the absolute most important is to clear memory. At this point, let's create a dashboard. So inside the dashboard is all of the hard-coded numbers. We should control most everything of our code through the dashboard. So one of the things we have to define is the function and its limits. I'm going to hit return a bunch of times because I don't like typing code on the very last line of the editor function. It does not behave well for me. So we're going to create a handle to weird func. And that way, if we ever wanted to do this same thing, but for a new function, we just change this one line of code. I don't have to go throughout the rest of my code and type in a new weird func or anything like that. We'll give it our 2 starting points. We had initially, was it minus 5.4 and a minus 5.3, I believe. And we may modify that to better visualize the method. But that's where we started last time. That's where we'll start this time. We need some secant method parameters. We need a tolerance, and we'll call that 1 times 10 to the minus 7th. That's what we used last time. Okay, so before we get into visualizing it, the first thing I like to do is actually write the secant method and make sure that it works. And we could copy and paste from last time. I'm going to choose to just type it from the beginning and explain everything. So secant method. And so what we hope we do is we find the root. Once we have a working secant method, then we can add the graphics to it. So following the block diagram and what we did last time, the first step is to evaluate function at x1. So f1 is func at x1. At this point, we'll enter into the main loop. So we're going to have a while our increment from iteration to iteration is greater than a tolerance that we defined, then do everything that's in the while loop. So we have to start off with this increment. I'll set it to infinity to begin with. So of course that's going to be greater than any possible tolerance we could define. And we may want to count iterations. So let me just say iter equals 0 to start from the beginning. Okay. And our first step inside this loop will be to evaluate the function at x2. So f2 equals func x2. How are we doing? We're doing pretty good. Let's just run this to make sure, well, it will freeze because we're not erroring out of the loop. Okay, let's finish the algorithm and then we'll run it. Usually I like to run things a few little lines of code at a time. And if I really wanted to do that here, what I could do is say break, and that'll break out of the while loop, and I'll just make sure I don't get any syntax errors or something. Okay, so all looks good so far. Now we need to calculate dx. This will be the increment from iteration to iteration. So dx is f2 times x2 minus x1 divided by f2 minus f1. Go ahead and run it again to make sure there's no errors. Looks like we're good so far. Adjust points, and we're copying information over from the second point to the first point. The second point from our previous iteration becomes the first point in the next iteration. So x1 is x2, and I don't want to reevaluate the function because we already have it. Let's keep in mind that function might take a while to reevaluate. All right, calculate new x2. So x2 is the old x2 minus the increment. And we might want to keep counting iterations. So iter, man, I cannot type. Iter equals iter plus 1. Let's go ahead and run this, make sure it doesn't get any errors. All right, let's take the break out, and let's see if we converge to the root. We'll type in x2 because that's the actual guess at the root. Okay, and we got the root from last time. So we have a working secant function. Now we're going to have to go in and modify the algorithm even a little bit for the purposes of visualizing. So what I'd like to do is plot all the iterations that we want into a single figure window. So we're going to do a bunch of subplots, which means we need to define some stuff up in the dashboard. We need to define how many iterations it is that we want to visualize. So let's put that under secant method parameters, n_iter. Now let's visualize, how about 6 iterations? And if we wanted more, we could certainly put more in there. Okay, so we'll go back down to our graphics, what will become our graphics. And probably the first thing we should do is clear the figure window, CLF. And we haven't plotted anything yet, so there shouldn't be anything there. But you know what? If we change our minds and we do something before this, we want to clear it. The next thing, we're going to want a bunch of subplots. So let's calculate subplot dimensions. So the number of subplot columns, I'll call that NSP. Let's make that 2. And it could be 3. 2 or 3 works pretty well. Let's stick with 2. So we'll have 2 subplots wide. And then how many rows of subplots? You know, I don't know because it depends how many iterations I'm calculating. So let me calculate number of iterations over however many wide, how many subplots wide we have, and we'll round up so we have enough rows. So that'll be columns of our subplot and how many rows for our subplot to do this. Now each iteration, we're going to want to plot a nice smooth version of our function so we can visualize our discrete points on it. So let's go ahead and do that. Let's calculate a high resolution function. So XH for high resolution, linspace. Now what limits should we do? Well, let's just do an XA and an XB right now. And we'll do 1,000 points for a nice smooth function. That's probably too many, but this calculates quick enough. We don't have to worry about it. We have to give some thought of XA and XB. So really, these are going to be the limits of our x-axis. And we would like limits that are wider than our actual discrete points so we can visualize everything in a nice little window. And so let's go up and make another heading. Let's call it graphics parameters. So we need an XA, and maybe that's a, I don't know, minus 5.5. We can come back and adjust this, and we definitely will because it's probably too much, and maybe a minus 5.2. That's comfortably outside of what it is we're visualizing here. But we might find out that for better visualization, we might want to tweak some of these numbers just to make it look better. But we'll come back and do that. Okay, so we now have our super high resolution x-axis, and we will evaluate the function. We'll have a high resolution function, so we'll call that FH equals func XH. So now we have something we can plot, and let's go ahead and do that then. So where should we put our stuff? we have to give some thought of maybe how we're going to modify our algorithm. And if we want to show the points from the previous iteration and the points from the next iteration, well, we don't want to do it after we adjust the points because then we've just lost the information from X1 and F1. So really, somewhere around here is where we need to add our visualization code. So maybe we'll just call this ready the subplot. So we will say subplot. So how many subplots tall? That's MSP. How many subplots wide? NSP. And which one are we plotting to? Iter. So iter is going to go 1, 2, 3, 4, 5, and we know that we're counting iterations, but I think at this point it does not make sense to use a while loop because we're not taking our algorithm all the way. We're only doing a certain number of iterations. So why don't we say something like for iter equals 1 to big N iter, because we only want that many iterations. And then we also don't need to count our iterations. Right? We're not actually running the algorithm to convergence here. We're just running it to visualize a certain number of iterations. Okay, we're going to plot a bunch of stuff. We're going to plot lines, we're going to plot points, we're going to plot a projection on here, a whole bunch of stuff. So I want to say, hold on, that'll freeze the graphics. And somewhere down here, we will need to do a hold off. I'll type that now just so we don't forget, but we'll do all our graphic stuff in between here. Okay. Now, we do want to plot our next point on this same plot. So strangely enough, this is going to happen up here, but we don't want to overwrite x2. So what I'll do is I'll copy this code. We'll calculate new x2, but we will call it next, right? And so then down at the bottom, we'll call it adjust points. Now we want to adjust our points, but this last line is just x2 will be equals x2 equals x next. So we modified our algorithm a little bit. It works, but we had to do that because we actually want to plot information for both the previous and the next iteration. So it forced us to have to do that. We can go ahead and run this just to make sure we don't get any crashing. We see a bunch of blank subplots. We see that that's working. 2 subplots wide, 3 subplots tall, because that's we're visualizing 6 iterations. Okay, so what's next? Well, let's go ahead and plot our high resolution function. Plot high resolution function. So we will say plot XH, FH. We'll do it with a solid blue line. And let's make the line width 1. We don't want to make it too thick here because these are actually somewhat small subplots. Let's go ahead and run that. And at this point here, I think we want to adjust our axis limits a little bit. So let's do that next. So we will say xlim, and we're going to go from XA to XB, which we did in our dashboard. And while we're at it, let's run it and come up with a YA and a YB to fix our Y-axis limits. So, okay, we'll save that. Now we'll go up to our dashboard, and let's come up with a YA and a YB so that we can have a comfortable amount of space above and below our function. So YA, if we're looking at our axis limits, I mean, we have a 10 to the minus 3 here. Maybe we want something like minus 0.1 times 10 to the minus 4, and maybe a maximum value of, oh gosh, 2 times 10 to the minus 4. Let's give that a try for our y-axis limits and see what happens. So we'll do a ylim, ya, and yb. Go ahead and run that. And well, it looks like we went off the curve a little bit, but I have a feeling we'll be adjusting our x-axis limit. So let's just leave it right there for now. And we can adjust that after we add our points to fine tune. I think we're close enough. Okay, so what is next? We plotted our high resolution line. Oh, what? You need a title. So why don't we, while we're here, let's just add the title to count the iterations. So we have iteration and num to string iter. Go ahead and run that and make sure now we have our iteration number at the top of the plot. All right, that looks pretty good. The next thing I would like to do maybe is plot the discrete points. We have our x1, we have our x2, and then we also have our x next. So we actually have 3 points. Let's go ahead and do that. So plot discrete points. So we'll do plot, lowercase, plot. We just want 2 points here, and so we'll just do x1 and x2. We know the function values here, f1 and f2. And let's draw these as just blue circles, not connected by a line. If we wanted to connect them by a line, which we don't, it'd be a dash. So we're just going to do a blue circle for each point. And we'll make these really thick circles. So line width, we'll go a little bit thicker and say 2. Let's go ahead and see how those look. Yeah, they look pretty good. Now, I don't like my first iteration starting like this. I probably would like, just for aesthetic appeal, I would like these points to be a little bit closer. So already I know we're probably going to want to adjust x1 and x2 just for more appealing graphics. But let's continue and plot some more things. We need to plot the next point. Plot x next. And here, we just want to plot the projection. So we want to put x next on the y-axis. So we'll just put in a 0 there. And we'll do it as an X, a red X. And again, we'll make it sort of thick so it stands out. And see what that looks like. Okay, we had a red X almost on top of that point. So yeah, we definitely want to adjust that because that does not look good. We want a different X1 and X2. Okay, so let's now draw a line across at the y equals 0. And we'll do that here since that last point is on that line. So the line's going to go from all the way from the left side of the plot to the far right side of the plot. And we want it to be y equals 0. So we put zeros in for y. And let's make it a dashed line. See what that looks like. Notice what I'm doing. I'm looking at things as I go, and I'm thinking, okay, I want to add this. I go back and I add it. Okay, at this point, let's adjust our points a little bit. I would like x1 and x2 a little bit closer. So that way it'll just make for a more interesting visualization. So maybe let's make x1 maybe minus 5.31 and x2. I guess we'll stick with 5, but I'll add a 0 just for aesthetic appeal. Let's see what that looks like. Yeah, I like that. I think we're doing pretty good. And now we can imagine a line going through these 2 points, and there's our projection. So that's maybe the next thing we should do. Let's draw this line, which would be our slope projection. So we'll scroll down in our code, and we'll call this step draw projection. And this is pretty easy. We don't have to do too many fancy calculations. We already have XH, right? That's a super high resolution array going from the extreme left side of our plot to the extreme right side. We don't have to calculate a new thing like that. What we can do is just calculate a projected line, so FP, F for projected, and we're going to use just the equation of a line. So we'll have F1 plus, we need a slope, XH minus X1. So we need to calculate the slope, but we have our 2 points, rise over run, so it's F2 minus F1 divided by X2 minus X1, so that's our slope. That should give us our line, and then we just need to plot that. Plot XH, FP, and we'll make it a red line. Now, this line is going to go way off our plot, right? Because we plotted all the way to over here, but since we're setting our axis limits, the line would just look like it stops here because we clipped our y-axis limit. So we really don't have to worry too much about that. Let's go ahead and run that, and there's our slope projection. See that? So here's our 2 points, there's our slope projection, and then we're showing our next point. At this point, we would eliminate that point, and we'd have a new point over here, and we slowly walk toward, we're looking pretty good here. What else could we do? Well, let's say I am grading this now. Well, one of the first things I notice is there's an inconsistent number of digits along the x-axis, and that's not pleasing to the eyes. And I would also look along the y-axis, but it turns out that's not a problem here, so we don't need to fix that. But I think we do need to fix it along the horizontal axis. So this is a minus 5.45, so it looks like we're doing 3 digits. So we need to make this also 3 digits and make everything 3 digits. I would like to retain MATLAB's ability to automatically place the tick mark, so I don't have to keep thinking about that. And so let's use the tick marks that MATLAB automatically generates for us. All right, let's go ahead and do that. So after draw projection, we'll call this x-axis tick marks. So let's go ahead and get the tick marks that MATLAB is currently using. So get current axis, x, tick. T will now be an array of those tick marks, and it's going to go minus 5.5, minus 5.45, all the way up to minus 5.2, or whatever we happen to do in our plot. So let's initialize our text labels in a sequence. So these are curly braces, not brackets. So we need a sequence of strings that will be the labels. All right, and for m is 1 to length of t. So for each number, we're going to loop over all the numbers in t, however many that happens to be, and then define this string, and that's num to string. We'll give it the number that we want to convert, and then the format. And so we'll do %4.2f, and that gives us consistently 2 digits each time. Now, if we don't do anything else, we wouldn't have done anything. We're going to have to go back and say set get current axes x tick label with an L. And now if we run this, that should automatically, we made a mistake somewhere. We misspelled num to string. So num to string. And we'll run that. Okay, now we have a consistent number of digits along the horizontal axis. At this point, I'm looking at a bunch of wasted white space here. So I think we could do better in terms of our x-axis limits to sort of zoom in on this a little bit more. So let's make a better guess. Maybe we can use something like, maybe minus 5.45, so we won't go quite too far to the left, and maybe a 5.28. Let's try that, 5.28. If we don't like it, we can change it. I think that looks pretty good. Maybe we could come in a little bit more, but I'll leave that to something that you can play with. All right, I'm looking at this. The next thing I would pick on as an instructor is that we don't have either of these axes labeled. And so that's horrible. We need to go in and label those axes so that the person looking at this knows what they are. And I guess we could just do that after the hold off. That's fine. So label axes. Let's see, X label. We'll label the x-axis as X. And let's go ahead and run that. See what that looks like. Now, the next thing I would pick on is that's a standard X, and that's not proper formatting for a math variable. That is X. That is a math variable. So really in MATLAB, we need to be using the LaTeX interpreter for this. So we're going to go in there and type in interpreter LaTeX and go ahead and run it and see what happens. Well, it changed the font, but it's not italicized. Math variables are always italicized. And that's because we haven't told it that's a math variable. Stuff that is math, we want to put inside dollar signs. Go ahead and run that. All right, now we have a nice italicized X. Let's go ahead and copy and paste this for the Y label. And of course, the Y-axis we want to label with a Y. And we can run that. Now, this is a very short label. That should not be rotated like that. That looks sloppy. It's rotated because in default, maybe there's a longer label here, like maybe we would say Y-axis or weird funk or something that's longer, but we just labeled it Y, and so it's sloppy to keep that rotated. We don't want to do that. We are much better than that. So rotation 0. And run that. That looks good in terms of rotation, but now notice it's crammed up against the numbers. We don't like that. And that's because by default, it center justifies. We need to right justify that. So let's go down to the next line. So I'll do comma, dot, 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 and we need to control its horizontal alignment, and we'll give it right alignment. Now, if we run it, that Y thing should not be crammed against it. That's good. And by the way, if this seems like a lot of work, it is at first, but from this point forward, you can copy and paste this code into all of your future plotting routines. So I think that looks pretty good. If I was going to do something else, I would probably use the text command and label these as X1, X2, XR, or perhaps I copy and paste this into like Adobe Illustrator or Inkscape, and I add my annotations there. Either way is fine, but I think this is pretty good. We got the secant method working, then we added the visualization, and we saw we had to tweak some things to make it look really good. The very last thing I might pick on is font size, but I don't actually know if these fonts are too big or too small. I would have to paste it into my document and see, but let's just pretend that they're too small because that's usually my complaint. And so maybe we'll just say set GCA font size, and maybe 12 will look good. I don't want to go real big here because I have a lot of stuff on my figure window, and that looks pretty good. But as I mentioned, you're going to want to copy and paste this into your document to figure out whether those are actually big or not, because you might reduce the size. And you could do other things like play with the size of the figure window, and then maybe that would force you to then go in and adjust font size or other things. But I think we did a pretty good job of visualizing the secant method, and I hope you find this helpful.